Geometry, note section 8.1, simplifying radicals. This is an algebra review, but that being said, I don't know how much time you spend on it in algebra, and this is not the easiest concept, so it's important that we review it. So here are some guidelines, which are not rules. This is one method that you could do this. You could make a factor bush, and then find perfect squares or pairs and square root them to move them outside the radical. We're going to go through this. Multiply all inside numbers together and multiply all outside numbers together. So I'm going to actually do this a little bit differently than what I just said there. Let's write down some perfect squares. So 1's a perfect square because 1 squared is 1. 4 is a perfect square because 2 squared is 4. 9's a perfect square, 25 is a perfect square, 36 is a perfect square, 49 is a perfect square, 64 is a perfect square, 81 is a perfect square, 100 is a perfect square. A perfect square means that you can take a number, an integer, and multiply it by itself to get this answer. 1 squared is 1, 2 squared is 4, 3 squared is 9. I left out 4 squared. 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared, 8 squared, 9 squared, 10 squared. We could continue. So one method of simplifying these radicals. And once again, this radical symbol, if there's no little number written in this little location here, it's implied that it's a 2, which means what number can you multiply it by itself to get 18? Now, the answer to that question is an irrational decimal. Irrational means that the decimals never repeat and never end. So we want to simplify this as best we can. And what that means is we want to make sure that every factor of 18 that's a perfect square gets simplified. So if we look at these perfect squares that we wrote down up here, can we divide any of these numbers into 18 evenly? And the biggest number we can divide into 18 evenly is 9. So we could rewrite this as the square root of 9 times the square root of 2, because 9 times 2 is 18. This 9 is a perfect square. What is the square root of 9? What number times itself gives you 9? Well, that answers 3. 2, its square root is an irrational number. It's not an integer, so we just leave it inside the radical. I am suggesting that 3 times the square root of 2 is identical to the square root of 18. If you square 3, you get 9. 9 times 2 is 18. It's the same as square root of 18. Let's try the same method for number 2. See what happens. Can we think of a number, a perfect square that goes into 28 evenly? So just looking at the closest number to 20, it's a perfect square, is 25. 25 go into this evenly? Nope. How about 16? Nope. How about 9? Nope. How about 4? Sure. So we could write this as the square root of 4 times the square root of 7. Now notice on the last one I put them both inside the same radical. Here I put them inside their own radical. You can do it either way. Do you know what the square root of 4 is? What times itself is 4? Well, that's 2. Is 7 a perfect square? It is not. Are there any factors of 7 that are perfect squares? Other than 1, there isn't. 4 doesn't go into it evenly, and 1 does, but it's being left with 7. So this is 2 square roots of 7. That's equivalent to the square root of 28. Number 3, we have a number already on the outside of the equation, or on the outside of the radical. So we leave that number on the outside. So let me show you a different way to do this. The first two methods, the first two problems we did, we used the same method, which is we tried to find a perfect square that was a factor of the original problem. A factor is just something you're multiplying. For this one, I'm going to take 27 and I'm going to make a factor tree. 27 breaks down to 3 times 9. A factor tree, you keep breaking these numbers down till they're prime. Prime means you only have two factors, one in itself. 3 is prime. Let's bring that down again. 9 breaks down to 3 times 3. So the prime factorization of 27 is 3 times 3 times 3. This is going to get you the same result had we used perfect squares as factors. It's just a different way that some people might prefer. Once it's prime factorization, since this is a square root, we want to circle pairs of the same number. If this was a fourth root, we want to circle groups of 4 of the same number. For every pair, you put one of those numbers on the outside. So we already had a 3 on the outside. This blue 3 represents the 3 that was paired, the 3's that were paired together. Let me do this. And then the leftover 3 that had no pair stays on the inside. Now, as it says here up above, multiply inside numbers together and outside numbers together. So our outside numbers are 3 and 3, which is 9. Inside numbers just 3. This is 9 square roots of 3. We could have done the same problem how we did previous ones and say that this is the same as 3 times 9 square roots of 3. Pardon me, 3 times the square root of 9 times 3. Square root of 9 is 3. Leave the other 3 inside, and this is 9 square roots of 3. Two differing processes to get us to the same result. Number 4. Let's see. Looking at our perfect squares, does 100 go into this evenly? No. How about 81? Nope. How about 64? Nope. How about 49? Nope. How about 36? Yes. 36 will go into this evenly. It will go 3 times. What is the square root of 36? It's 6. So this is 6 square roots of 3. If you don't like that, here's how we could have done it. We could have broken 108 into prime factors. We can divide this by 3. It's going to go, let's see, 16 times, I believe. Is that right? That's not right. 108 divided by 3. You know your handwriting's bad when handwriting recognition software doesn't recognize your handwriting. Oh, I know what I need to write. That doesn't recognize the division symbol. 36 times. I was not close. I don't think that's what I said. So anyhow, well, we accidentally got to this right here. Oh well. Continuing, 3 is prime. 36 is 6 times 6. 6 breaks down to 2 times 3, and so does 6. Since it's a square root, we circle pairs of the same number. We got a pair of 2's, we got a pair of 3's. For every pair, you put one of those numbers on the outside. Anything uncircled stays on the inside. This ends up being 6 square roots of 3. Now I know what you're thinking. I won't want to do it that way. It's too much work. It's fine. Do it this way. Do it this way. I don't care how you do it as long as you're doing it correctly. As a matter of fact, I don't even need to see the work for you to get full credit for this. I just need you to do it correctly. Now, number 5, if you look at this carefully, it's saying, what's the square root of 5 squared? Square root means what times itself gives you this number. Well, what times itself gives you 5 times itself? Well, this is obviously 5. If you don't like that, 5 squared is 25. What's the square root of 25? It's 5. No matter how you look at it, it's 5. Number 6, these are letters. So it's x times x times x times x times x. 5 of those, because the square root means, this exponent means you're multiplying this base by itself that many times. Pair of x's, pair of x's. For every pair, you put one on the outside. Anything that's unmatched and unpaired stays on the inside. So this is x squared times the square root of x. These ones here, we are multiplying radicals together. And the order in which you do these things then doesn't matter. I've got some guidelines written here that you can follow or not follow. What's important is that we get the correct answer. It says first multiply each separate radical if needed. Notice it says if needed. Then multiply numbers on the inside together and outside together, and then simplify again if needed. Well, let's check this out. I could just simply leave this as, hey, I got a square root of 3 and a square root of 3. I have a pair of 3's, so I put 1 3 on the outside. There's nothing left over, so it's 3. Another way that you could look at this, if you prefer, put them both inside the same radical. That's the square root of 9. What's the square root of 9? It's 3. Same answer. Number 8, order of operations here. We are supposed to, first of all, this squared only applies to what's in the parentheses. So the answer is going to be negative. If you square the square root of 3, that means you're multiplying the square root of 3 times the square root of 3. As we just saw, that's 3 with the negative out front. If you prefer, you could write this as negative square root of 9, which is still negative 3. Once again, don't care how you do it as long as you do it correctly. Number 9 is a very similar problem, but it's different. I'll put this here intentionally. 8 says, take the square root of 3, square it. When you're done, change the sign. 9 says something a lot different. It says, take negative square root of 3 and multiply it by itself. So this is going to be a negative square root of 3 times a negative square root of 3. A negative times a negative is a positive. I'm putting the plus for emphasis. And as we've just figured out in the last 3 problems, the square root of 3 times the square root of 3 is 3. If you want to write it as square root of 9 first, that's fine. So this just becomes 3. This problem has to be negative every time. This problem has to be positive every time. Number 10, wow, we are lousy with 3's. We are squaring the 3 and we're square rooting it. Those are inverse operations, so we get 3. That is the same problem as number 7. It's just written in a different way. Number 11, square root of 3 times square root of 2. Let's say we make this into prime factors. It's already in prime factors. There are no repeating factors, so there's no pairs. So all we're left to do is multiply those together and we get square root of 6. Now number 10, if you use the first method I showed you and you say, well, what's this? Is there a factor of 10 that's a perfect square? The answer is no, because its factors are 1 and 10 or 2 and 5. Is there a factor of 2 that's a perfect square? The answer to that's also no. So it appears as though this is just square root of 20, but it isn't. I'm going to do this in 2 different ways once again. If we break the 10 into prime factors, it's 5 times 2, and then we already had this other 2 here. Hey, we got a pair of 2's, so that's 2 square roots of 5. Another way to look at it is to multiply the 2 and the 10 together and get 20. 20 is 5 times 4. Square root of 4 is 2, so you get 2 times 5. Either way is fine. Don't care how you do it. Division. Guidelines. First, if it's possible, divide the radicands together. Radicands are what's inside the radical, and numbers outside the radical together. Then simplify each separate radical if needed. Finally, simplify again if needed. It's not the greatest guidelines, to be honest with you. Can we divide both 27 and 3 by the same number? The answer is yes. Since they're both inside the radicals, we can do that. We can divide both those by square root of 3. Square root of 27 divided by the square root of 3 is square root of 9. Square root of 3 divided by the square root of 3 is 1, so it's square root of 9. What is the square root of 9? It's 3. Different way to do this is to break the square root of 27 into prime factors. 3 times 3 times 3. And if you wanted, you could write this as square root of 3 times square root of 3 times square root of 3. These are identical, just different ways to write them. We could then say if we divide the square root of 3 by itself, they cancel, means if you divide them you get 1. We're left with square root of 3 times square root of 3, which I believe we understand is 3. Number 14, let's see if I can divide the square root of 6 going to square root of 48 evenly. Sure does. Go square root of 8 times. Square root of 8 is square root of 4 times square root of 2. Square root of 4 is 2, so it's 2 square roots of 2. Number 5, we got some outside numbers. Can you divide both 8 and 5 by something other than 1 and it go evenly? No. How about 15 and 3? Yes. Square root of 15 divided by the square root of 3 is square root of 5. And then square root of 3 divided by square root of 3 is 1, so it's 1 times 5, which is 5. Now we might be finished. Here's what you need to check to make sure if you're finished. Is this radical simplified? Yes. Can you simplify this radical with a radical on the bottom? No, there's no radical on the bottom. Can you simplify 8 divided by 5? That answer is also no, so it's finished. Number 16, I can divide square root of 11 into square root of 55. It's going to go square root of 5 times. If you divide square root of 11 by square root of 11, you're left with 1, which we don't typically write if it's on the bottom. This is simplified radical, so that's our answer, 11 square roots of 5. Rationalizing the denominator. First of all, when do you do this? If your answer has a square root in the denominator, we don't like to leave our answer that way. So this is the process that you do to fix that. Excuse me. First, try to simplify with division. So that means like we did over here. We simplified with division and we didn't have to worry about it. So can we simplify here with division? No. If there's still a radical in the denominator, which there is, multiply by 1 in a clever form. So please keep in mind, if you multiply by 1, it doesn't change the value of what you're multiplying by. A way that we could write 1 that would be helpful for this is to write 1 as a fraction of the same thing over itself, of something over itself. Now, why is this helpful? Because in our numerator, 1 times the square root of 3 is the square root of 3. In the denominator, square root of 3 times square root of 3 is the square root of 9, which is 3. We have just rationalized our denominator. It no longer has a square root in it. Can this be simplified? No, because the 3 is inside the radical on the top, and on the denominator, the 3 isn't inside a radical. And this radical is all the way simplified. We are done with this problem. Number 18, we have a radical in the denominator. So to fix it, we're going to multiply by 1 in the form of square root of 2 over square root of 2. It's going to give us square root of 2 over square root of 4, and the square root of 4 is 2. It's finished. Number 9, hey, we got a radical on the top and the bottom. Can we divide both of these by the same thing evenly other than 1? And the answer is no. So let's multiply it by the square root of 3 on the top and the bottom. It's the same as multiplying by 1. It's going to give us the square root of 24 over 3. Now we're not finished. It looks like we should be finished. You can't divide these because one's outside a radical and one's inside, but the square root of 24 is not simplified. We could write the square root of 24 as the square root of 4 times the square root of 6, because 6 times 4 is 24. Why would we choose this pairing? Because square root of 4 is a perfect square. That's going to make this 2 square roots of 6 over 3. It's now finished, You can't divide 2 and 3 by the same number, by the same number other than 1. You can't simplify the square root of 6. We are finished. Finally, number 20. I'm going to multiply this by square root of 2 on the top and bottom, same as multiplying by 1. And I get square root of 22 over 2. This radical, if you break it into prime numbers, you get square root of 2 times square root of 11. There's no pairs. And this is on the outside of a radical, so we can't simplify it this way, so we are finished. Please do the homework assignment that corresponds to this from the web.